Okay, well, welcome again to the Europlanet Science Congress in Granada in Spain. This is our third press briefing and final press briefing of the week, so we're delighted that you can join us today. Today we have a whistle-stop tour of the solar system. We're going to be going from Jupiter to Mars and then to the Moon, and we're going to be looking at some of the exciting new ways of exploring and visualizing planetary environments. So we're going to be starting off today with Gerald Eichstäd, who is an independent citizen scientist who will be talking about new processing of images from JunoCam. Then we are going to Sebastian from the Freie Universität in Berlin, and then who will be talking about a hiking map of the Jezero crater on Mars, and then finally we'll be going to the Moon, to Patrick Bambach of the Max Planck Institute for Solar System Research, who will be talking about the LEAP Lunar four-legged robot, and then Giacomo Nodjoumi of Jakobs University in Bremen will be launching the Explore Lunar Data Challenge. So, Gerald?
So, hi, good evening, everyone. I'll talk a little bit about cloud height estimates on the basis of JunoCam images. JunoCam is the education and public outreach camera of NASA's Juno mission to Jupiter. On this first slide, we see a typical JunoCam image taken during Jupiter's page of 43 flyby. JunoCam is able to take sequences of images covering a common area. During earlier perijove flybys, we observed Jupiter from a similar perspective over up to about 1 hour. Such observation series allowed us to derive animations and measurements of the motion of Jupiter's clouds. Now the next slide. More recent perijove flybys allow for a qualitatively different kind of image sequences. Those sequences change the perspective onto a common area rather quickly within a few minutes. They are essentially long baseline observations. Long baseline observations are particularly useful for parallax measurements. When you stretch your arm and watch your thumb while focusing to the background, and then switch between your left and your right eye, your apparently jumping thumb is a parallax observation. Cloud motion is less significant during this new type of observation campaigns than it has been previously. Next slide. With an accurate alignment, enough statistics, and some geometrical calculations, we are able to perform such parallax measurements. One of those measurement results is shown here. We get an elevation difference between two cloud layers of about 15 kilometers. A similar measurement along the same front system returned a relative elevation of about 22 kilometers. Next. The JunoCam has 4 color filters attached to its CCD chip, a red, a green, a blue, and a narrow methane band filter around 890 nanometers. We can visualize the value of the red channel of that image I showed first as the elevation of a landscape. This movie shows a flyover animation over such a landscape. Bright cloud features correspond to hills, darkish cloud features correspond to valleys. The landscape corresponds very roughly to a tentative model of Jupiter's cloud topography. Images taken around the 890 nanometer methane absorption band would be better suited, but they are rather noisy. Therefore, I used the red channel here instead for illustration purposes. The missing ingredient is a translation of this brightness landscape into physical elevation data. My presentation here on EPSC is about an approach how to retrieve elevation differences in units of kilometers. Those elevation data can then be used to calibrate cloud top brightness landscapes like this one in terms of physical elevation. With more parallax measurements together with methane band images, we think that we will be able to retrieve a highly resolved 3D model of larger areas of Jupiter's cloud top topography. Such a 3D model can then be compared to theoretical models of the condensation of some of Jupiter's chemical species, especially ammonia, ammonium hydrosulfide, and water in the clouds. I thank you. Next one.
Thank you.
Okay.
So can we just hand over now to Sebastian and we'll take questions at the end.
Hi, my name is Sebastian Walter. I'm working at Freie Universität as a planetary geologist and I take off the mask. Thanks. And as such, we are used to work with maps, and maps help us to find overview of the areas and locate the data we have acquired. Here you see a map of the Jezero crater, where the rover landed more than a year ago. And this rover is producing tons of data sets every day, and it's very hard to locate these data sets. And that's what the map's purpose is, to help in locating the data set and to really coordinate the way we can look at it and help get a visualization of the data. And we prepared, please back to the, not yet, yeah. We prepared that map as a hiking map, because actually we started with that before the landing of the rover, and we used the orbital data from existing cameras to create data sets and virtual 360-degree panoramas to create a view how someone who would fly there above the surface would really view the surface at that time. And here you can see these white droplets, and when you zoom around in this map, then you see more of them, and everywhere you see such a droplet, you can click on the map, and then you get transferred into this 360-degree panorama and see that in 3D, or if you have virtual reality headset devices, then you can even see these landscapes in virtual reality. And the rover has also a microphone on the SuperCam camera, and the sound is also used here for these panoramas. But I forgot one step, because after the landing of the rover, the Mastcam Z camera on the mast of the camera of the rover is starting to produce and to upload a lot of data, and they are creating real 360-degree panoramas in an unprecedented detail. The recent one was from more than 1,000 single images, so the single image itself is not so big, but they acquire the images in a way that they can stitch them together to a really 360-degree panorama. And then it was very lucky that we already had the infrastructure to have a very good way to visualize them. So now could you please this is the system design of this application. So it consists of a front end and a back end. The front end is the user's browser, so you don't have to download anything, you just open the website, and then you have to probably, depending on your internet connection here in the conference center, hundreds of people are using the internet at the same time. It's a little bit slow, but usually it should load up in a couple of seconds, and the data is all sitting at the server and is streamed to the client as tiles, so that makes it performant, and whenever you zoom in, you get new tiles, but only the ones you are currently demanding. Please, could you go on? And yeah, now I did some screenshots. Maybe we can even, if you volunteer to test the map, yeah, we can switch to the Chrome browser. Oh, this one over there. Yes. Yeah, you're right, there's the zoom menu, but I think we get an idea. There's nothing important up there. So yes, you can zoom around by dragging and clicking and with the mouse wheel. And on the left you see like a menu, and there you have layers, right? And here you can turn on and off the different layers. you see that the rover pass points are they are actually pulled live from the GPL website, and when you further zoom in, you see that the topography is even covered in very high detail, and at some point it switches to a no, I think it's already the highest detail, but yeah. So here you can really see the single stops of the rover, and whenever you have such a droplet, you can click on that, please. Yes, that's the landing site actually. So that was the first panorama which has been submitted. Yeah, and now we have the effect of the very slow internet. So maybe we go back to the slides because these are. Was it? Now it appeared. Okay, yeah.
The full screen.
You can do the full screen again. You can even go on this mask, on this VR mask on the left. Yes, this. Then it goes to complete full screen. And we can't hear that now, but there's even the sound from the microphone involved. You can see the rover. I think you're now zoomed in already. If you use the wheel, all right. And yeah, you can enjoy this fantastic images. And I think the only way to get back is, yeah, you click on this map icon and then you get on the
back
left. Yeah. And yeah, you can also directly jump to another scene if you click on this I button. Below the layers, below the I, like the organ, yeah. And there is you have these are the synthetic ones we have created from orbital imagery. So these are CTX high-rise images. Co-registered to HRC and color-coded also by HRC because these instruments usually don't have color channels. And yeah, it's very useful for scientists or even the public to have a very immersive experience of how this crater looks like. And yeah, that's a synthetic view of how the possible paleo lake could have looked like at that time. So we reconstructed the water level and included a lake. And maybe you can also switch on the last and most recent.
This one?
Yes, this one. Probably it will load a little bit, but it's really worth it. This is the last panorama from Mastcamp Z. It's only a couple of days since they have released it. And you can even see, if you go to this bright stone there. So you have to watch the ground.
Sorry.
Yeah, you see this bright, and now if you zoom in there, you can see the drilling of the sampling. So there is they have taken a sample. I think it was actually not successful, but they still could do a lot of science with these drilling. If you're in this room, you can even hear the sound of the rover. I think it's not transmitted to the broadcast, but this is the real sound of the rover when it's moving. It's from the SuperCam instrument. They have the first working microphone on Mars now. So we included that, and you can imagine if you put on the VR device, it gives you really a nice feeling. Thank you very much. Proof that without an experienced web user, you can get along. And there information about, also if you click on this I button, yeah, exactly. There's some information about the sites. I think that's important.
Yeah, okay. I mean, we saw already great pictures from rovers, and I want to just add one more picture of the rover opportunity. It's just proving how incredible science and how the picture of the of Mars changed through the eyes of rovers, of wheeled rovers. But actually, this picture also shows one shortcoming of wheeled rovers, that a lot of times scientific interesting sites are located on spots where wheeled rovers can't really get. So it's on steep slopes, or behind boulder fields, or some other areas where rovers unfortunately cannot go in direct contact. And to solve that problem, we started a mission study on, next slide, which is called the LEAP rover. Actually, it's a four-legged robot And with this mission study, we wanted to prove that we can do science in one of the most interesting lunar area, which is the Aristarchus Plateau, and which is hard to access, but would deliver incredible results. So if you look on the next slide, this just gives you an impression on how the lunar surface is looking like. Actually, top left, it's an Apollo picture, and it shows you how like lots of boulders may block the way of a rover and how steep the slopes can be on the moon. And on the top left, you see, for example, a high albedo area, which can only be reached after crossing like more than 20 degree of a slope. And on the bottom left, bottom right, you see like multiple collapsed lava tubes and cracks in the ground, which allow to study subsurface material, but which are hard to reach with a wheeled rover, but which is possible to get to with a LEG system. But the LEG system has not only the advantages of its mobility, there's more. If you go to the next slide, maybe there's a video.
Reinforcement.
There it is. So
Our controller is capable of autonomously recovering from a fall.
So you can maybe choose more risky approaches. A LEG system has joints which rotate less than 360 degrees, so you can seal them against lunar dust, which makes them a little bit more reliable. And even if one leg fails or two legs, a robot still can walk on even two legs. And now in this picture, you can even walk on wheels, but maybe you don't do it on the moon. But there's more. As soon as you have legs, you can use them in addition to your instruments. So if you look on the next slide, just like some animals give us some ideas what you can do with legs. So you can dig, you can flip stones, you maybe even can hit probes. So you're able to manipulate with them, which is pretty useful because the top layer, for example, of the moon, it's space weathered, and it's interesting to see like a little bit beneath the surface. Where are we? So if we, next slide. So just on the progress, the LEAP project is based on Animal. Animal is had been developed by the ETH Zurich. It's an industry-grade, industrial-grade off-the-shelf maintenance robot. And in 2019, the ETH started to test it in a lunar environment, and the progress was pretty fast. So in 2021, they qualified for the finals of the ESA asterisk of the Space Research Challenge. And currently and ongoing, we are trying to adapt the hardware for a lunar environment, so in terms of lower energy consumption on thermal management and so on, to be eventually able to get to the moon. And LEAP is part as a topical team, which is an ESA program to look for payloads which can launch on the European Large Logistic Lander, which is supposed to land multiple times at the end of the 2020s on the moon. How to learn to walk on the moon, on the next slide. There's three main issues. You have to adapt to the terrain, to the lunar gravity, and to the lunar soil. The terrain, you can find similar ones on Earth. That's easily doable. Gravity is tricky, of course, if you want to change it in the real world. And actually also the soil is an issue. There's simulants, which are similar to what we found on the moon, but unfortunately due to the different gravity, we cannot have all the properties of the lunar soil on Earth, because the damping might be correct, but then the strength which causes avalanches on slopes, for example, is wrong. We still try. So on the next slide, actually we put one of the robots on the, maybe there's a video, but yeah. We put the rover in the Mars testbed where the ExoMars rover was tested for walking on high slopes. So even this simpler version of the LEAP robot managed to go on the full elevation immediately, and it also is to be able to work parallel to the slope. And if we go virtual, on the next slide. So the rover learns walking in a virtual environment, and their gravity is just a constant, so that's easy to solve. If it comes to soil, yeah, on the left side, you can see how the rover is running up actually a slope, and you can see the legs disappear. So this is kind of us simulating like collapses and avalanches. And the left side, you see like a little bit the damping and the sinking in of the rover when it walks on the moon. So we try to incorporate the soil properties. And on the next slide, you can see the results. This is how the rover is walking on the moon, or at least our simulations. Actually, this is how it's always learning. So you train him in the virtual environment, and then you load the software, and it will eventually then directly walk in reality. So here he's crossing a realistically modeled boulder field of the moon, going through a crater, and continues to go on. And actually, we swapped the videos because this is the rover rather jumping. And you can go to the next slide, which is no, sorry, back. No, back. There's two videos, but I don't know. Okay, never mind. Then go back to that one. Yeah, you can just press play. So actually, there was a video before where he's not jumping around most widely, because if he's asked to walk safely, he would not jump around. But he's doing this. If you ask, if you ask him to do it more energy efficient, he will just immediately start jumping around. And yeah, this kind of made us confident because this robot is not the first AI system which started jumping on the moon. So if you go on the next slide. Actually, the Apollo astronaut found the very same solution, that it's more to
this is the best way for me to travel, uphill or downhill.
To jump on the moon than
What's that?
to
Like
simply
this?
walk.
Two-legged hop?
If you go to the next slide, just simplified, when would you use it? So if the terrain is simple, flat, you may choose a rover with wheels because it's more energy efficient and maybe less complex. But if the terrain becomes more complex, you might choose a system with four legs, which can cross boulder fields and get up slopes. And if you even want to climb in caves or get up like more than 45 degrees, you may even go to a system with 6 legs. And if you have even more energy and even want to do more complex stuff, maybe on the next slide, you may choose a system with 2 legs again. But yeah, they can go hand in hand because actually the robot can also carry stuff for astronauts and whatsoever. So maybe they even make it together on the moon. So yeah, I hope I could introduce you somewhat how the system learns to walk and what it can do. And I hope that it will be seen on the moon soon.
It's open? Okay, thank you. I will present the two data challenges that we'll be launching this year, actually now, right today, if I remember well, and are on the moon, of course, and then are specific for experts and juniors and classrooms, and we'll focus on the detection of craters and boulders on a specific region of the moon that we'll show you in a few moments, and then create a transverse, like to simulate a possible transverse to be performed by human rover or automated rover, and then find the best possible solution among different points of interest that will be among in this traverse. So for everything, please join us in the exploredatachallenges.space website and follow the hashtag Explore platform and Explore Moon Challenge. And yeah, I will just show now the So this is actually the site of interest, briefly. So this is a region in the northern part of the moon, and it's really challenging to be analyzed because there are quite a lot of data of different, from different part of the electromagnetic spectrum. And the data is, the area is quite challenging because there are a lot of rills, mounds, craters, and so it's a peculiar area to be analyzed by man-made mission or by a human, by a rover, automated rover. And we have set several points of interest. This is only a demonstration of a possible transverse and possible point of interest, in which each point will have like the name of this point and the type. Like we would like to collect and simulate a possible real mission. Like you will take some navigational images, some geological samples, and you will use some different instruments. So the base of the challenge will be that first, the participant will detect all the possible features that may compromise the path of the rover or of the rover, and then try to find the optimal path across those points and risk areas, trying to collect most samples as possible. They can choose whichever method they want, from machine learning, deep learning, or other kind of manual approach, and we will accept everything, and we will evaluate on different base scoring levels about like how many points have been reached, how fast they reached those points, and how efficient the rover was or the man-made mission was. And that's pretty much it. So if you want to participate, just join us. And yeah, one thing that I want to mention is that the final results will be announced at the anniversary of Apollo 17, so late in this December. Yeah, join us. We will have several prizes. If I remember well, there will be like a grant to buy equipments. I don't remember exactly the amount, but there will be several prizes. And there should be also a piece of the moon, if I remember well.
There's a piece of lunar meteorite.
Yeah, a lunar meteorite, sorry. So, yeah, there are some interesting prizes, but yeah.
Right. Well, unless we have any questions for anybody, or if any of the other panelists would like to ask each other anything else, then in that case, thank you so much for joining us today, and thank you so much for joining us at the Europlanet Science Congress in 2022. Next year, EPSC is going to be joint with the DPS, with the Division of Planetary Sciences of the American Astronomical Society. So we're going to be in San Antonio, Texas, from I think the 1st to the 6th of October. And then in 2024, we're going to be back in Europe, in Helsinki, towards the end of September in Finland. So that's it for the media briefings. There will be the media releases for all of the presentations will be with you. They're on the website already, but they will be with you later today, and there will be more media releases coming throughout the week. But thank you again for tuning in, and if you do have any questions, then please feel free to contact us via email or Twitter or however you would like. And thank you very much to all the panelists today. So thank you.